Okay, guys, I was explaining this before the session timed out, and we had to go to this. So on getting this, because once you have this, you can now take these two. If you look at this equation here, when you take these two, what happens is you have this system here. Then you have this minus this, which is 0. But we know that this one is uy and this one is vx. So that gives us the second equation, which is this one. And after getting those two equations, remember we've decoupled a second order into a first order PDE. And in decoupling, what was a second order into multiplicities of first order differential PDEs, we have come up with this system. I'm using two words here: coupling, decoupling. If I call this one equation 1 and I call this one equation 2, I can actually couple these and I go back to the original second order differential equation. This is what you did in DIFFERENTIal. In DIFFERENTIal, you have second order, you break it down or you decouple it and you get two linear differential equations. Or if it is a third order, you break it into first, you get three linear differential equations. So it's the same thing here. And if you decouple and you get these two, then you can go back to our elementary algebra, matrix algebra. So once you have this, we can actually try to rearrange this one here. The best would be rearranging. You know how we write matrices. So if you take it in terms of A and B, so you have, this is the generic form we are using. This one here. You all know that if you have your differential equation, rather system of ODEs, you can write it explicitly as some form AX, which is equal to a certain B here. Okay, so you have that one. You have all of these. This is some constant kind of column matrix. That is for the right-hand side. And then you can generate the matrix A here. But now here, what is going to happen, since we have two independent variables, X and Y, this is only in one variable. Of course, here, the X here could be a matrix, maybe say M, comma N. Is that okay? This one could be a 2 by 2, which is, this could be a square matrix or a rectangular matrix, but you know when you're dealing with this kind of computation, you usually deal with a square matrix. So this can be some M by M or N by N. So here, since we have X and Y, this notation, when we talk of A, carry U, carry X, and B, carry U, carry Y. This is the A is a matrix, the B is a matrix. And where are we picking these matrices? From here. So if you try to look at this, this is UV, and then this is UV. Is that okay? So we have a V and we have a U. This is U, this is V. So that's why you have UX and VX. Now here we are going to strictly go back to our linear algebra 1, and I hope no one is going to get issues here. So from here, the coefficient of, you remember matrix multiplication. You multiply a row by a column. If you multiply this row by that column, then you know that you can pick the coefficient. The coefficient of UX here This ux is the 1 minus m squared. Is that okay? Then remember that when you come to Vx, in here, there is no Vx. If you look at this one here, there is no Vx, implying the coefficient of Vx here is 0. That is where you get this 0 here. So when you multiply this by that, it should give you this, because you'll have this times this plus that times that, which is 0. So we don't have Vx in equation 1, therefore that's 0. Then when you come down here, we have again, if you go by what we have here, ux, in this second one here, ux does not exist. It is evidently clear that in here there is no ux. If you look at this one here, there is no ux. What you have is Vx. So coefficient of ux is 0, but when it comes to Vx now, this Vx here, it is a minus, therefore you have a minus 1. Okay, then we go to the next one here, uy, vy, we go back again. You realize that here there is no uy, so the coefficient of uy is 0, but we have a vy is 1, which is that one there. Then we go to the second one here. You have uy here is 1, the coefficient of that is 1, but there is no vy here, therefore the coefficient of vy is 0. And this is 0, we equate to 0. Okay? That one is that. All right. Then what we have, someone is saying, oh, I think I agree with you. I need to activate and you get those notes. I have seen a comment here. This is, it is Aguero Solomon. Yes, Aguero Solomon. I can see you are saying the notes are missing on Mwere. I will activate. But I must also assure you, most of your colleagues already have those notes. That is why they have not said anything. But since you want to get them from Mwere, I'm going to upload them. As if we are missing the notes, Doctor, upload for us the videos. See some of the lecture collide with the others. I don't know what that one is talking about. This one is saying refer to numerical analysis too. Okay, that one I have not followed. Whatever they are discussing, they know better. Okay, so from this, we can now go ahead and solve. Now, guys, you surely remember very well if you're dealing with EIGEN values and then EIGEN vectors. So you have your B minus lambda A, which is equal to 0. And you are going to look for the EIGEN values. So you have that matrix and you have this matrix. For each EIGEN value, you get the corresponding EIGEN vector. And for each corresponding EIGEN vector, you can deduce. There is statements in here, but I don't know whether I have really to dig much into this. But nonetheless, you have this and you have that, and you can now substitute to get the EIGEN values. And you remember, so if you have your A and you have your B, so get this matrix, get that matrix there. So here you have the lambda, which is more of your identity matrix, and you have this one here. So basically what you have here, it is this matrix. I'll just, interest of time, I'll just do this. So you have this matrix here, which is the B, I hope we are together. Now you are going to subtract the lambda A. The A is this one here, which is 0. This is lambda, and you have lambda, and this is 0. So you have this matrix here. Okay? So if you do that, what do you end up with? Basically, you're going to have this one minus lambda. Of course, rather this is this one, then you have minus lambda here. This is minus lambda, and this is 1. So you're going to have 1 minus, this is m squared. Remember now it is element-wise. This will be what? This one will be minus lambda here. Then here element-wise, this minus this one is also minus lambda here. And then you have a minus 1 here. The parameters. So this is what you have. You are computing the determinant of this one. And that is equal to 0. And you remember the determinant, you take this one here, leading diagonal. So when you take this negative into that, that becomes m squared minus 1. I'm leaving out the subscript of this chi infinity, but you know it is there. So when you take this one here, you have this times that, which is that. This is already positive. This will be minus lambda squared. I don't know whether you guys are with me. What is in the chat? Okay. I hope you guys are following me. So this becomes m squared minus 1 because our leading diagonal, this one here, or the principal diagonal, you have this negative which will change the order of that one, hence the m squared minus that. Then for the secondary diagonal, which is in black now, this and this is already positive, okay? But remember we subtract. So because we subtract, this will be the zoom is home. Where are you physically? Let me come. I'm winding up a lecture. Okay, this is minus lambda, guys. So I think I can confidently put this one in brackets like this. And of course, as always, this is squared. As always, now we remove the sign for determinant because we have already computed the determinant. But why don't I omit these things? Because these things, you know, you guys. Can I hear a yes in favor of omit that? I see some yes, doctor, yes, doctor. I don't know this yes or why is the response to what? I've not understood the yeses. Guys, I have a request. What I am doing here is really the obvious thing. Maybe we can omit this one. So it means here your m squared minus 1 is equal to, what is this? This goes to the other side. This is a square. And of course, when you take this one, it means your lambda will be plus minus root 2 of m squared minus 1. This is how you are getting these roots here. I don't know whether we are together. You have lambda 1, you have lambda 2, square root, square root. Where is the negative 1 coming from? As if I don't see this negative 1 up here. I don't know whether I have made some mistakes. Okay. But doctor, it's like you made an error. Maybe I made an error somewhere. This is in whatever Albert, but he has not pointed me where. Some guys enjoy saying yes, but you can leave that for us. Yeah, I think this is really. Then the negative 1, addition is, sorry, someone was trying to follow me up closely. This is in whatever. I don't know whether I have made a mistake, but surely there could be a mistake. But at least You just compute the EIGEN values. These are the EIGEN values, and you remember now how to get the EIGEN vectors. And for the EIGEN vectors, we still use this same definition. But the only difference here is with the EIGEN vectors, now it will be B minus lambda. This is A. Instead of computing the determinant, this one, we can maybe have some epsilon here. In this case, we are using eta. So you have some eta. You have this, which is a 0. So at the end, you end up with this matrix of B minus that. Then you'll have your eta 1, sorry, eta 1. Then you'll have eta 2. And this will be equal to 0, 0. And the best way to deal with this is you go back again in linear algebra of solving systems. The best approach here would be to do row operation. You operate and you remember where you would have parametric systems. You have the number of non-zero rows versus the number of variables. Then you know whether the solution you have is unique, or it has multiple solutions, or the solution does not even exist. This is purely just linear algebra, one that you can throw here. Someone says, no, whatever, you got A, B instead of BA. You could be right. This is a whole, no, whatever, you could be right on that. I may have mistakenly interchanged that. You could be right. That's why I was looking for a certain negative. Okay, so if you go ahead, you'll get these. I have told you how to arrive at these ones. Simply go. And the easiest way, okay, use any approach, but for me to get these, I usually just, like this one, I just did the row operation. And in doing the row operation, you easily get the EIGEN vectors. Why are these EIGEN vectors different? You first compute for one with respect to lambda 1, and then you get one with respect to lambda 2. So what you see here is for lambda 1, these are to do with the lambda 1, and then EIGEN vectors associated with the lambda 2, they are these ones. Okay, yes, I have actually observed that Noah Sasira Ronald, yes, I made a mistake and interchanged the matrices, which was more of commuting, and that was not correct. But the bigger picture here is people have got the concept, and now that they know the concept, now you know that we can solve PDEs using those concepts of linear algebra. And why we are interested in a space here, or this EIGEN vector, the EIGEN vector caters for the space or the field in which this dynamics of the PDE takes place. Okay? And that field can be also characterized. And here, that's why we are drawing conclusions about that field. Okay, so we are saying that's the system depends on whether this is bigger, equal, or smaller than 1. Of course, we are looking at the nature of the root here. You know that for you to get it as real and complex, it will depend on whether m squared is greater than 1 or less. I hope we are together there. So when we talk of m being less than 1, these are complex in nature, and we are saying the system will be elliptic. And in this case, we say it has a subsonic flow. These people doing physics, I'm sure they have done fluid dynamics. And this is simply a narrative helping the people doing math that ran away from physics what a subsonic flow is all about. Okay, And if m squared is greater than 1, then we are saying it is what we call a hyperbolic or supersonic flow. And remember, we talked of the convective kind of equation. This one lies under that behavior. If you remember when we talked of the types, I hope I don't have to go really too much behind to, yes, this advection equation is directly associated with this supersonic flow of this hyperbolic nature. And here we are saying that the stream of that fluid will be perturbed in such a way that if it was supposed to be downstream, it will change direction to an upward or stream motion. And if it was upstream, then it would be downstream. This is heavily applied, by the way, in what we call environmental engineering. You know, in Bulisa, we are busy drilling oil. So all of those catastrophes that are mitigated, usually they try to use PDEs in getting solutions to these catastrophes. Then, of course, if it is equal to 1, here you get a parabolic system, which is a transonic flow. And we are saying both will be equal to 0. Now, there is something very important about what we have discussed. Yeah? For those who have understood, you have done your best to understand. The kuramas, they are also there. We looked at the other conditions that can be satisfied. But sometimes when you are given a system such as this, you can as well use, because here you have UXX and you have your UYY. So you could use the discriminant we talked about earlier. But now you realize here still the discriminant comes in the form of the term under the root there. But now there are some systems where if you try to use the first discriminant, the terms that come out, it may not be easy to conclude whether it is positive or negative. And by the nature, and I'm sure you did even this in dynamical systems, when Dr. Juliet introduced to you the concept of the Hawes criterion of looking at the EIGEN values, and then you could deduce whether a system is stable or unstable, and when it could descend into a saddle form, but using the Ruth Hawes criterion of just analyzing the EIGEN values. So in that case, you would also realize that you would look at the discriminant, you look at the coefficients of the characteristic equation, and then there are some conditions that had to be satisfied. In this case, you will find that if the nature of the coefficients you have, if substituted into that discriminant, give an expression where there is too much interplay in terms of the negatives existing there, and you may probably not be in a position to simplify it to a conclusive approach of knowing that this is positive or negative, then this approach we have just discussed here would be quick and fast in giving you a conclusion about the behavior of that given PDE equation. I really hope you have got me here, because sometimes this could be paused and you are not told which approach to use. And the choice of which approach to use will heavily depend on how you have comprehended the subject matter. All right. I hope you've got me on this. Okay. That is that. Then for the one-dimensional flow, you can go and you do these ones. Same story. This is one-dimensional flow, but this is second order here. You decouple it into first order. Decoupling that into first order, you get this one here. And after getting that as the first order form, okay, you go ahead and you get this matrix here. You go ahead and you solve, get the eigenvectors from each of the eigenvalues that has been obtained. And on doing that, you come and you draw the conclusion. It has only one eigenvector, since two of the eigenvalues with only one corresponding eigenvector, you deduce that the system is parabolic. I hope we are together there. Right. Okay, we have analytical solutions of PDEs. Can you guys hear me? The silence is becoming too much. Can I see a yes in the chat? All right, at least people can hear me. The weather is very conducive, so you should be able to some rain. I don't know where this man diction is. You're supposed to be in your villages. So I hope when you say rain, the rain is in the village, not in the Makerere. If you are here illegally. Okay, we can continue. Okay, this is, by the way, here there is nothing. When you talk of a solution to PDE and a function independent variable, when we talk of a solution, you know, it is not difficult to show that this is that one. When they say that to show that this is a solution of this one here, it means you're going to differentiate, guys. Let's not waste time here, really. You have this one here. If you have U, it is given by that. Then you show that it is a solution. It means you're going to differentiate this thing twice with respect to X. You substitute here. You differentiate again this one twice with respect to Y. You are doing a partial differentiation. Is that okay? And you can see that is what is done here. That if you have this, you have maybe this is this another example? No, we are dealing with this one. This is what we are having here. I hope you see this one comes to that. Okay, UX, it is you differentiate with respect to X, it is a 3x plus Y. Remember, when you differentiate the inner term, it gives you 1. Then UX, it gives you this 6 here. It gives you the 6. Then with respect to Y, you get this one. With respect to Y, similar story. And when you do that, when you go into the substitution, you realize it is going to be this one here, which is 1. Okay. And you deal with this one, which is 2. When you substitute these 2 into this equation, not into that one, but rather if you substitute them into this equation here, you get 0. I'm referring to this equation, this thing comes that way. Okay, so those ones are not really a big deal. Okay, people are still complaining about my network. I hope, guys, you can hear me. Really, can you hear me? Can you hear me? Guys, can you hear me? Okay. They can, someone no. When someone says no, you know that one is lying. This man ejection. If it is a no, how did you hear the question? When I say, can you hear me? And I get a no and a yes, it means you can all hear me. So the ones saying no, you can also hear me. Otherwise, how did you get the answer to the question if you did not hear me? It is impossible for you to say, no, you don't hear me, yet you have heard the question. Okay. The same story happens here. Show that this one is that one. Thus, this one is a solution of that one. So once you have this differentiate, substitute into that one, see what comes out. That is what we are doing here. This is petty stuff here. Show that the given function is a solution to the given partial differential equation. I assume that these ones are constants. You do. You're simply showing that this one here, is that okay? Satisfies that one there. So these are so basic for you people. Even the Kurama would walk away smiling if this one came in an exam. That is sure that what I have highlighted here is a solution. Just to differentiate. Okay. And that is basically it. I don't see us wasting time here. That one finished. This one is finished. All of these ones show that this one is a solution to a heat equation. The only thing that the Kuramas are going to suffer with, the Kuramas, is if they have forgotten how to differentiate a function like this one. What matters is, do you know how to differentiate something like this? That is what is important. So what are you going to do to show that it is a solution? You are going to, first of all, differentiate this thing here with respect to t. Partially, you will differentiate it with respect to t. Is that okay? Differentiate this one with respect to t, or call it, you did the differentiation operators. Then after, you will differentiate it twice with respect to x. You will look for a dxx. Substitute here, or take this one minus the other one. Is it 0? You deduce that it is indeed a solution to that one. All of these ones, go and do the coche, Riemann. Once it is coche, these ones usually come with differentiation, and again, sometimes you may have some imaginary related kind of functions. Okay, that is all to do with that. Yes, method of characteristic equations. We are remaining with how many minutes? The minutes, they are around 5.5. Maybe I can introduce this one. Okay, so we could start this one next week, given the time, but I could probably introduce it. So when we talk of these methods of characteristic equations, first order, you have this. Here we are going to bring in Lagrange. You guys did Lagrange, I think, in the numerical methods. Numerical analysis one. Numerical analysis one, you looked at the Lagrange approach of handling some polynomials. Okay, so in this case, we are saying if you have a linear PDE involving a dependent variable u and the two independent variables x and y, you already know what is dependent and independent. We have overly explained that. Then, okay. Okay, this man, Nakundo, Peter, may you talk about the test? You people, I am also excited. You know, when you find the people very excited about the test, you also become excited. The test, we are going to do the test. The only issue, maybe let me first respond to, okay, let me use, we are remaining with something like 3 minutes. We are supposed to have a test on Saturday. But that time there is another test that is going to be running. So either we shift the times. I had wanted to have the test early in the morning, but that test has questions I don't want to remove, and we have not yet covered them. So I think we can postpone it. Reason number one is I prefer having those tests early in the morning. That is 6 to 7, but 6 to 7, there is another test that is running on a Saturday, and it has a very big group. So I am afraid if I add on this big group of around 260 students during the same time slot, Mwere may misbehave. That is reason one. Reason two is reason two, and now reason two comes to Mr. Ayevare Nicholas, who says we can have it on Sunday, a very brilliant idea. But reason two is I will not have finished some of the questions that I'm already having in there with regards to PDEs that I want you to do. So for now, we can say same time, Saturday next week for the test. I don't know whether I am clear there. These people who are online. Okay. So because Sunday would be fine with me, by the way, I could even have chosen Saturday from 4 a.m. But people will tell you network, but they think I am an idiot. Even those who say network, it is not about network. You want it during the day so that you cocoon in one room and you copy, and you give the same answers. They are not going to be physical tests. My tests are all going to be online. You will do the exam physical tests, Mwere, blended assessment. So all of the tests we are going to do them on Mwere. You are not going to have physical tests in my subject, at least. We together, guys. Mwere is here to stay, and I am saying you are going to do them virtually, online. Is that okay? It is blended, and it is better you also familiarize yourselves with this blended app. Right now, people are defending their PhDs virtually. They are this way, and because there is too much COVID still abroad there, everything is virtual now. So please, we are not going to have physical tests. The tests are all going to run on Mwere. The exam, physical, even the exam section A, I am still trying to see if section A can be done on Mwere. Then section B, you do it physically on paper. But section A can purely be on Mwere. I am trying to see if that can be possible. Mwere, but under supervision. Okay. So the test next Saturday,